This lesson objective covers refrigerant properties of R134 alpha. That'll be the refrigerant that runs through our vapor compression refrigeration cycle. We looked at the ideal refrigeration cycle in the last lesson objective, where our compressor was isentropic and the condenser and evaporator were both isobaric. We know from the first law analysis that the work required to run the compressor is the change in enthalpy from state 1 to state 2. We then know that our heat rejection is our change in enthalpy from state 3 to state 2s. Our adiabatic expansion tells us that our enthalpy at 3 is equal to the enthalpy at 4, and then our heat addition to the system is simply the enthalpy at 1 minus the enthalpy at 4. So everything we're looking for is a function of enthalpy. But where do we go to find that value? Well, it's very similar to the vapor power cycles where we have tables or a figure. First, we'll look at figure 2 in your reference manual. That's all the way after all the tables, starting with figure 2, where this is the DuPont Fluorochemicals HFC 134 alpha chart. First, we'll look at the enthalpy for BTU per pound mass. So we have enthalpy as kilojoules per kilogram for our SI units, and then next we will have enthalpy for BTU per pound mass for figure 2E in your reference manual. So now this is in the English units, where we have pressure in pounds per square inch, actual, referencing enthalpy as BTU per pound. So if we start, we have our vapor dome shown here, and this is similar to your pressure versus enthalpy diagram in figure 10.2 in your textbook. Next, we have lines of constant pressure and constant enthalpy. Pressure runs horizontal across the chart, and enthalpy runs vertical across the chart. Next are lines of constant temperature, which come down, hit our dome where we have our saturation temperature, in this case our saturation pressure, then across down along the side. Then we have constant enthalpy, which runs from the bottom left to the upper right. So where your constant entropy would intersect your state, you could follow that constant entropy line to the next state, and that would give you then your enthalpy at the second state. And finally, we have constant specific volume, which runs along the bottom. How's the other way we can do it? Well, if you look in tables 14, 15, or 16, you will find tabular data for HFC 134 alpha. So at 200 kilopascals and 80 degrees Celsius, we start off at table 15. This is the equivalent of table 11 for the steam tables. So at table 15, we enter at 200 kilopascals. We see that our saturation temperature is significantly less than our actual temperature, therefore we're in the superheated region. So now we turn to the page to table 16, reference the table that starts at 200 kilopascals, find 80 degrees Celsius, and find out that our enthalpy is 323.68. So now we've solved our enthalpy for the state we were looking at. So in this case, our enthalpy would be 328.68 kilojoules per kilogram. This could be our superheated state at state 2 right after the compressor. The other way to do it is if we use that DuPont Fluorochemicals chart. So using figure 2, we know that our pressure is 200 kilopascals. Our chart is in megapascals on our vertical axis. Therefore 0.2 megapascals equals 200 kilopascals. We enter our line of constant pressure at that state. We look for our temperature of 80 degrees Celsius starting here. We follow that line until the intersection. Read straight down, and we find that our enthalpy for this state using this chart is 465 kilojoules per kilogram. You may see a discrepancy in this. The last chart said we were at 323 using the tables, so the tables tell us we're at 323 kilojoules per kilogram. Now this chart tells us it's 465. There's a discrepancy. Well, you're right. The tables provide one enthalpy, while the DuPont Fluorochemicals provide us with another. Basically, the scientists that did the two charts used different starting parameters to solve this. So Both charts will give you the same change in enthalpy. So if we were solving for the power going into the pump, it would be H1 minus H2S. So we'd solve H2, we'd find our H1, and we'd get a change in enthalpy. If we did the same thing on the charts, we would have the same change in enthalpy. So the big takeaway is our change in enthalpy. That's what we want. How much did the enthalpy change? Where the tables will give us lower values, but the change in enthalpy will be the same between the two experiments. The main thing is do not mix the charts with the tables. If you start with the charts, finish with the charts. If you start with the tables, finish with the tables. This completes the lesson on how to find your enthalpy for refrigerant 134. Have a great day.